Okay, so going from the formulas to the names. We've done all the pieces that we need to do it. We've done the learning. We just got to think about what it means to go backwards. So I put up here binary ionic compounds. What does binary mean? Binary means 2. So binary compounds are going to be something with 2 elements in them. 2 capital letters in the formula. Everything you did yesterday was binary. Make sense? Okay, ionic. Ionic means it's made up of ions, a cation and anion. Okay. And one of the things I hoped you noticed on the back of that homework was that to write the name at the end, all you had to do was copy the names from the beginning. Because the name of the end, at the end, was just the name of the ions. If I put together aluminum ions and chloride ions, I get aluminum chloride. And you drop ions because now they don't have a charge. Because compounds are neutral. Always put the positive piece first, cation first, anion second, metal first, non-metal second. Okay, now, as long as everything's in group A, as long as we have nothing but representative elements, it is really easy to do. You did it last night. If I gave you NaCl and asked you to name it, what ions are in NaCl? Well, there's an Na plus and a Cl minus. Na plus is called the sodium ion. Cl minus is called the chloride ion. Put them together and it's called sodium chloride. Metal first, non-metal second. So when they say sodium chloride, they're talking about the ions are sodium ions and chloride ions. MgBr2. If I ask what ions were in MgBr2, you'd say there's an Mg with a 2 plus charge and a Br with a 1 minus charge. There's 2 of the Brs with a 1 minus charge, but those types of ions I have to worry about are Mg2 pluses and Br minuses. Magnesium ions and bromide ions. So the name of the compound is magnesium bromide. Pretty simple system. Okay. But usually about this time somebody raises their hand and says, "Oh, excuse me, Mr. Green. What about that 2? Nowhere in the name do you mention that 2. And that's because I don't have to. Because if I ask you to write the formula for magnesium bromide, you're going to write Mg2 plus and you're going to write Br minus, and you're going to say, hey, that doesn't add up to 0. I need to do the crisscross, and I'm going to put that 2 right there. And if it's easy to figure out, it doesn't show up in the name. So scientists are lazy. They want to write the bare minimum that lets you go back and forth. And this math is pretty easy. So there's no need to put it in the name. The other reason is that most often when we deal with these, they're dissolved in water and the ions have fallen apart already. So if you have a solution of magnesium bromide, if you dissolve magnesium bromide in water, what's in the water is water, magnesium ions, and bromide ions. Right? So you're describing the active pieces when you dissolve it, which is where you use it most often. Does that make sense? So write the name of Na2S. Well, here's where we start. Na is a metal. Okay, well, why would I start there? They're all metals. They are when we're doing ionic compounds. We've got other kinds of compounds to name that have completely different rules. Right? There are a completely different set of rules out there. So we need to decide which set of rules first. So first I say Na is a metal. Okay, it's ionic. Na is in group 1A. Doesn't need Roman numerals. So I can just write sodium. The negative piece of this is S. S is sulfur, but the negative pieces I change the ending to ide, so this is sulfide. So the name of that is sodium sulfide. Pretty easy? Told you, group A's are easy. What do you do about the transition metals? Okay. Because transition metals, for all but 3, the cation has a Roman numeral in the name. Right? I can't say iron ion. I have to say whether I've got the iron 2 ion or the iron 3 ion. So if I want to write the name of them, I'm going to have to figure out the charge on the metal. So how do I do that? I mean, I can't get it from here. Where can I get it from? Well, if you're trying to write its name, they gave you the formula, right? And you know that the compound has to be neutral. That's why we dropped the word ion off of it. And neutral means the same number of positive and negative charges. I'm trying to figure out the positive charges. What I'm going to use is the negative charges, because I always know the negative charge. I always know the negative charge, so I can figure out how negative it is, and use that negative to figure out how many positive, what the positive charge has to be. So I use the negative charge to find out the charge on the positive ion. Some integer math. Making sure the total positive equals the total negative. So let's give a few a try. I ask you to write the name of CuO. Okay, so I start off, Cu on the periodic table, Cu is a metal, this is ionic. Cu is a transition metal, I need the charge on copper. My first word is going to be copper. I need Roman numerals. How am I going to figure that out? Well, I know the O is 2 negative. So if this is going to equal 0, Cu has to be 2 positive. That's the only way it'll equal 0. And that's the charge on copper. So I call it copper 2 oxide. I know it's frustrating that copper 2 oxide does not have a 2 anywhere in it. But that's why they write them as Roman numerals. So you don't think that they're subscripts. Does that make sense? If they wrote that as an Arabic 2, you'd be really tempted to just copy it down. Right? All right. Let's make it a little harder. Name COCl3. Not a lot harder, just a little tiny bit harder. I find cobalt on the periodic table. It's a metal. It's a transition metal. It needs Roman numerals. So I got to use the negative pieces to find the charge on cobalt. So my negative piece is chloride. Chloride is 1 minus. I have 3 of them. So my total negative is 3 negative. So my total positive has to be 3 positive. So that cobalt has to be 3 positive if that's going to equal 0. Integer math? So everybody comfortable with how I figured out cobalt was I say my total negative is 3 negative because each one's 1. So my total positive is 3 positive, so that cobalt has to be 3 positive. How could I say the cobalt was 3 positive? Because there was only one of them and it was 3 positive. This was a little challenging because it had a subscript on the negative piece. We multiplied to figure out the total negative charge. What do you do? Well, call it cobalt 3 chloride, but all our trouble was figuring out the 3. And it wasn't all that trouble. Okay. What do you do when the subscript is on the one you have to change? When you're trying to figure out? Cu2s. Okay. Copper's a metal. It's ionic. Copper's a transition metal. I need parentheses. And it's copper something sulfide. Everybody okay with that so far? Hey, now I know sulfide is 2 negative. So my total negative is 2 negative. So my total positive has to be 2 positive. I've got 2 coppers that have to add up to 2 positive. How big is each copper? What plus what equals 2? Go with the obvious. It's 1, right? So the copper has to be 1 plus. So this is copper 1 sulfide. The 1's about the charge, not about how many there are. Because if we go backwards, if I gave you copper 1 sulfide, you'd say Cu is 1 plus, S is 2 minus. You do the crisscross and the 2 would end up on the copper. Okay? All right? Let's talk about the rust of the story. Oh, this is the formula for rust. See why we don't want to use rust as the name for this? What does rust tell me about it? Nothing, right? Fe2O3 tells me a lot about it. And the systematic name will tell me it's Fe2O3. Okay, now they both have subscripts. So each oxygen is 2 negative. You've got 3 of them. That gives me a total of 6 negative. That means I need a total of 6 positive. I've got 2 irons that have to equal 6 positive. How big is each iron? 3. Take the total charge, divide by how many pieces you have. So the name of this is iron 3 oxide. Reasonable? It works about 75% of the time. I mean, if I gave you this, you'd be tempted to say lead 2 oxide. But it's not lead 2 oxide. Because oxygen is 2 minus. It's a total of 4 minus. It's 4 plus. It's got to be lead 4 oxide. See, 75% of the time it works. And it worked on these cases because it was they didn't have to simplify. Okay. So let's try a few. KCl. K is a metal. It's a metal in group 1A, so it doesn't need parentheses. So I can just write its name. His name is potassium. Cl is the negative piece, so chlorine is a negative piece, is called chloride. The name of this is potassium chloride. It's got potassium ions and chloride ions. Extra super tough? about Na3N. Okay, Na is a metal. It's in group 1A, so it doesn't need Roman numerals. So I can just write sodium. N is nitrogen. As a nonmetal, we change one syllable and then "ide," so that would be nitride. And we're done. CRN. CR's a metal, but it's a transition metal. Its name is chromium, and I'm going to need Roman numerals. So I actually start right here by writing down chromium, Roman numerals. I don't bother figuring them out now. I want to finish writing names, and then I'll just go back and do the math. Nitrogen, well, right above, we saw what happens to nitrogen. Change it to nitride. Now we have to figure out the Roman numeral. Nitrogen is 3 minus. So in order for this to equal 0, the chromium has to be 3 plus. Okay with that? Following the rules? It's easy because there's no subscripts. SC3P2. Well, SC is a metal. It's right there, 21. It's a transition metal, so it's going to need Roman numerals. So that's scandium, something. And the P from phosphorus, I'm going to change that to phosphide. P is 1, 2, 3. P is 3 negative. Phosphide 3 negative. So I got a total of 6 negatives, which means I'll need a total of 6 positives. So I've got 3 scandiums that add up to 6. How big is each scandium? 2. So each scandium is a 2 plus. So that's what I write for my Roman numeral. That's the hard one. Was it really hard? You just have to remember to decide. Remember that I got to decide about whether I need Roman numerals or not. The Roman numerals are pretty easy to figure out. Okay, so now we're going to talk about your polyatomic ions. I told you have to memorize them. I'm going to give you some clues that maybe will help you memorize a little bit less and be able to figure out more. Because there's patterns on that list that you may not have seen. Last chapter, we identified polyatomic ions as groups of atoms that stuck together and had a charge. And last chapter, we drew them and saw how they were covalently bonded. Remember, we had to do the math because they always had extra or fewer electrons. That list I've given you, you have to memorize it. I got it off page 210 in your book. Okay. I've got the polyatomic ion quiz up there for Thursday. We'll use these tonight and tomorrow to give you practice with using them to see why you want to memorize them. Memorizing soon is better. Okay. So I get a little upset because when you look at the list, they put the nastiest one first. Acetate. Acetate is the nastiest one. You don't have to copy again. You've got a yellow list, so I'm not going to give you time to copy all these. What you want to take notes on is what's the patterns here. Okay. When somebody writes acetate, they mean those 7 atoms all together. Okay. Acetate only follows one of the patterns. There's only one clue in acetate, and that is the ATE ending. That ATE ending means it's got oxygen in it. It doesn't tell you how many oxygen, but it tells you it has oxygen in it. And for most of the things with ATE, the prefix in front tells you what's hooked to oxygen. Nitrate, the 8 tells me oxygen, the nitra tells me the nitrogen. Now, closely related to nitrate is nitrite. And this pattern happens a few times on the table. Well, there's an ATE version, then there's an ITE version. The ITE version means one less oxygen. That's what ITE means, one less oxygen. Happens a few times on there. So there's no sense memorizing nitrite. Memorize nitrate and you can figure out nitrite. Does that make sense? So I'm going to suggest that you memorize the root words and the rules rather than each individual case. Hydroxide. It's named backwards. It should be called oxhydride because they always write it as OH. Never HO. It's always OH. Permanganate. We see the AT ending that tells me about the oxygen. The manga tells me about the manganese. And we'll figure out what per means a little bit later. Per is telling me something else. Actually, per is telling me lots of oxygen. Cyanide, carbon and nitrogen. Almost spells its name out. Now, these are the two that end in IDE, and they're named that way because for a long time they thought they were elements. So when they found them in nature, they thought they were elements. So they gave them their own name like an element, and they found out they weren't elements. But that didn't change the name of the thing they'd chosen. Okay, then there's a family of them where everything's got Cl and oxygen. And you'll see in our family that chlorate is right there. That's the root. I think of the ATE version as the root. And then right below that is chlorite. Less oxygen. One less oxygen, same charge. The prefix hypo means even one less oxygen. So ite means take off an oxygen, hypoite means take off two oxygens. One for ite, one for hypo. And the prefix per means add an oxygen on. So in a place where it's on your list, but think about this. If I asked you to name O2 minus, you would call it oxide ion, right? Well, O2 2 minus is the peroxide ion. Peroxide ion. So per means one more oxygen. Now, I didn't give you a complete list, but I wrote down that bromate was BrO3. So could you figure out the formula for bromite? How about hypobromite? And perbromate? And all the halogens can do that. So there'd be an iodate. What do you think iodate would be? Iodate. 3. Yeah, IO3. All halogens act the same way. There's a bromate, there's an iodate. So that's the 1 minus ions. And some patterns. Memorize the 8 version and then vary from there. The 2 minus ions. Sulfate and sulfite. Now, sulf for sulfur, 8 for oxygens. Sulfite, sulf for sulfur, ite for one less oxygen. Carbonate. Han Solo is really happy that there's no such thing as carbonite. Because there was nothing to freeze them in. Chromate, chromium and some oxygen. right? Dichromate, the prefix di means 2, and it's almost twice as big. It's got twice as much chromium, Cr2, almost twice as much oxygen. That make sense? Oh, here's peroxide on the list, but that's how they got peroxide. They took oxide and added another oxygen to it. Peroxide. Oxalate, you just have to remember. Some are based on old names. 3 minus, there's phosphate, and then there's phosphite, arsenate. Well, it could be mean and give you arsenite. Now, these are not all the polyatomic ions. There are tens of thousands or millions of polyatomic ions. Okay, pick up a bottle. Look at the ingredients list. Everything that ends in an 8 and right is a polyatomic ion. Okay, positive ones. Positive polyatomic ions. These will start off the formula. Because positive leads, right? So you'll see these first. First one is ammonium. It's the most common one. Second one is only polyatomic because it's diatomic. When mercury forms a 1+ ion, it only does so as a it has to be 2 atoms stuck together. Each atom makes a 1+. So mercury 1 is Hg2 with a 2+ charge. That makes each mercury have a charge of 1. Remember, see how each mercury has a 1 charge? You'll notice that I didn't talk about all those ones that started with hydrogen. That's because they're not worth memorizing. They're easier to figure out. Because hydrogen ions are 1+. Right? So when I put hydrogen onto a polyatomic ion, it's going to change its charge by 1. And that's it. You're going to have hydrogen and 1 less charge. So since sulfate was SO4 with a 2 negative charge, hydrogen sulfate would be HSO4 with a 1 negative charge. Add the hydrogen, lose a charge. There is no reason to memorize hydrogen sulfate because you can see the sulfate part, right? That you should recognize. I can do the same with sulfite, right? I can do it with phosphate. Now it has to have a charge bigger than 1 negative for this to work, because I can't end up neutral and be a polyatomic ion, because I got to be an ion. Now, so I can add a hydrogen to phosphate and make hydrogen phosphate. Instead of being 3 negative, it's now 2 negative. But it's still not, I can still add another hydrogen to that. And I got to change its name because I can't call it hydrogen phosphate again. So they say there are 2 hydrogens and phosphate. Dihydrogen phosphate. And my charge goes from 3 negative to 1 negative. See why there's no reason to memorize the hydrogen ones? Because they're easy to figure out both ways. If I tell you hydrogen phosphate, you write phosphate and put a hydrogen in front of it. If I write you H2PO4, you'll say that's phosphate and 2 hydrogens. Dihydrogen phosphate. Hey, so binary meant 2 kinds of compounds, or 2 kinds of elements. Now that we have polyatomic ions, we can talk about ternary ionic compounds. Ternary means 3. Quaternary means 4. Okay. The only way you're going to have 3 elements in an ionic compound that you're going to deal with is that they're going to be polyatomic ions. You'll recognize in the formula because it'll have 3 elements, which means 3 capital letters in the formula. But all those rules that we wrote, that we did before, all apply. We don't do anything different. We just use a different kind of piece. So to name the compound, you still just name the ions. So, NaNO3. Na is a metal. It's in group 1A. It doesn't need Roman numerals. I can write sodium. NO3, polyatomic ion, called nitrate. So that's what I write. Yeah, got it. Not hugely different than what we're doing, right? About CaSO4. Well, Ca is calcium. It's a metal. It's in group 2A, so it doesn't need Roman numerals. SO4, sulfate. What ions are in this? Calcium ions and sulfate ions. Extra hard. So we kick it up a notch by putting in a transition metal. Copper's a metal. It needs Roman numeral though because it's a transition metal. If SO4 was sulfate, then SO3 must be sulfite. And sulfite had a 2 negative charge. So that means this whole thing had a 2 negative charge. So my total negative is 2 negative. So my total positive has to be 2 positive. This is copper 2 sulfite. Mistakes people made, they're tempted to write this 2 minus and then say it's got a 6 negative charge. Okay, but remember that O3 is not by itself. It's got to stay with the sulfur. This whole thing, including the 3, has 2 extra electrons in there somewhere. That's what we did with last time, right? Let's see why we don't multiply by the 3. SO3 is 2 minus, Cu is 2 plus. They add up to 0. What the heck is this? Open parentheses, NH4, close parentheses, 2O? How the heck am I? This looks like gobbledygook. Well, let's recognize some parts. I recognize the O, and it's second, so it's got to be oxide. NH4 is on your list. It's ammonium. Ammonium oxide. What about all those parentheses and things? Well, let's talk about why they're there. If I want to go the other way, ammonium oxide. O is 2 minus, NH4 is 1 plus. I do the crisscross, I'm going to have to write a 2 down here. NH42? That doesn't work, does it? So I erase that 4 and make it NH2. No. NH4 stays together. You don't get to change it. I need 2 of the NH4s. This whole thing is what I need 2 of. See the need for the parentheses? So I can't write the 2 next to the 4. I want to say I have 2 NH4s. So parentheses let me say I have 2 NH4s. Okay? You should always think of at least polyatomic ions in parentheses. Even if they don't have the parentheses there, you should think of that about them being in parentheses. As a unit, this chunk moves. It's a piece. Well, iron is Fe, and iron's a metal in the middle of the transition metals, so it needs Roman numerals. OH is hydroxide. Hydroxide was 1 minus. I had 3 of them. So I have a total of 3 negative. So my Fe's total has to be 3 positive, and there's only 1 of them, so that's got to be iron 3 hydroxide. Now, if you're going the other way, iron's 3 plus, OH is 1 minus. People are tempted to do the crisscross and write FeOH 3. But that says 3 hydrogens, not 3 hydroxides. Again, do you see the need for the parentheses? LICN? Li is lithium. It's in group 1A, so it doesn't need Roman numerals. Cn is named cyanide. So it's just lithium cyanide. Don't need Roman numerals. It's really easy. The hard part is figuring out the Roman numerals. Oh, the hard part is this. What the heck is this? Okay, well, NH4 is ammonium. CO3 is carbonate. So the ions that are in this are ammonium and carbonate. So this is ammonium carbonate. Is that right? Okay, that's all I got for today. Okay, I'm going to get this to you. And when I started this, I kept saying, get about 45 minutes of homework. I do not want you to spend more than 45 minutes on this tonight. If you're spending more than 45 minutes, something's going wrong. Okay? You should start speeding up as you do more and more of them. I mean, I can't think of these things taking a minute apiece to do. Can you? So if you're struggling, don't do more than 45 minutes of this. Right? Stop where you're at. I'll give you more time, but I need you to, because you're just digging yourself a hole along the way. Something's going wrong.